Okay, we go on with a lecture on class coding. And the part that is going to follow is maybe the one which requires most concentration. Maybe it's the most difficult, but it's really important. And when discussing with people, I found many people who told me, at the beginning for me it was a bit difficult to understand this error management. But now that I'm used to it, when I write a new C code on my own from scratch, the first thing I do is copying all the macro of class and go on coding in the style of class. So I was very happy to hear this. And so it's an effort to learn it at the beginning. But once you know it, it's very useful, very powerful. You can save a lot of time with it. So to motivate this part, you can do a run in an input file containing only this line. Omega b equals 0.07. Of course, it's a very crazy value. This is why I wrote it. Run class with this .ini, and you will get an error. And the error will look like this. And there is a lot of information. Error in thermodynamics.init. In this function at line 292, there was an error in this function. And then in this other function, in line 1031, this condition was true. You have asked for an unrealistic high value of omega b. The corresponding value of the primordial helium fraction cannot be found in the interpolation table. If you really want this value, you should fix helium to a given value rather than to BBN. So you understand the physics behind. It's what we said yesterday. By default, the code tries to figure out the helium fraction from this BBN interpolation table. We passed a crazy value of omega b. It doesn't belong to the interpolation table, so the code returns an error. So first, it's an error. It's not a crash. Okay. So the first thing you want to do when you write a code like this is that the code does not crash, because if you are running inside the sampler, Monty Python or Cosmosis, and if for some model the code crashes, it's your whole chain that crashes. You are very upset. And it used to happen very often with some competing codes. Now it has been improved. Okay, so you don't want the code to crash. You want the code to return an error. That's just a normal exit. You just have the information that it returned an error, but it's ready to go on with another model. And then you want to know where the error took place. So you see, this is a little bit like when you get an error in a Python script. Also in a Python script, you get all these tree of nested functions that led to the problem. All this should be generated automatically. So you see in this error message, if you search for this in the code, of course, you will not find it, because in the code, the only piece that was written is from U to BBN. All what is before, all this part, has been generated automatically by the error management functions or macros. So to arrive to such a result, you have to follow some rules. I think I defined 5 rules to follow, and I'm going to explain them slowly. Rule 1, you don't have the choice in the type of the function. A function must be an integer, and it must return either success or failure. So all our functions are always int. So success and failure are defined somewhere in command.h. They happen to be 0 and 1, but this you can forget, because you will always use the words success or failure. So at the end of a function, you always have the return success. But in the middle, there are some tests, and if the test does not work, there is a return failure. So this is rule 1. Rule 2. You don't call directly a function. You don't say function of input-output. You call the functions within a macro. And the most important macro is class call. I told you all our macro start with class. And class call is just the simplest way to call a function respecting the style of class. It takes 3 arguments, which is the function you want to call, a string that will contain the error returned by this function from here to here, and a string that will be used to pass the same error message to a higher level. And we will see examples. So class call is a macro, so it means it's a shortcut notation for something more complicated. And the something more complicated is written here. So when the code is pre-compiled, pre-processed, and it finds this, it automatically replaces the 3 lines by this bigger number of lines. And it does if function equal failure. So to evaluate this condition function equal failure, the code must call the function. So this is, in fact, where the function is actually called. It is called and it will return either success or failure. If it returns success, the if is wrong, nothing happens, it goes on. And then it was just like if we had written function and nothing else. If the function returns a failure, there are some lines here that I don't need to detail, which goal are to automatically add one layer of information of this type. So these lines are written automatically by what I showed you. So the goal is to say in which function and which line the error occurred, and to which function this line belonged to. Okay, so let's not go into the details of this, but you just have to understand that the macro here, or these lines of code, are going to write the error message written by this function in this field. And then, no, sorry, it's not this. Sorry. What happens is that when the function here returns an error, the error message is written here. So the code will take this error message, will add to it the automatic information, and will transfer the sum of the two to the error message output. So the error message output will contain the automatic line and the error message from this function. And this happens in nested sequences, such that at the end, you always have the final error message where the error really happens. And before that, all the tree of calls and functions that led to this. So you don't have to be very good in macros, and you don't have to understand this. Just at the end, you just need to remember that you will call your function within a class call. And I will tell you now, I will give you some practical rule for not making mistake on what you should put here and here. And if you follow this rule, everything will go automatically for you, even if you don't understand this. So now we go to rule 3. We say that there are 9 main structures, 9 and not 10, because I have not included the precision structure. In each of these 9 structures, there is always a field called error message, which is a string. So there is a PPT error message for the perturbation structure, or a PBA error message for the background structure. Any function called XXX something belongs to the module XXX and knows the structure of the module. And so any function belonging to the module XXX will always write its error message in case of problem in the error message field of the same module. So for instance, this function, perturb indices, is from the perturbation module. So it will always write its error in PPT error message. And this gives you the rule for the second argument here or here. You just have to see to which module the function that you are calling belongs. And you keep the error message of the same module here. This is a perturb function, PPT. This is a background function, PBA. Now, what is the rule for the third entry? it's equally simple. If I do this class call, I do this class call of the perturbation indices function, but I could do this class call from any other module. But here we assume that we call this function in perturb init. And then if we are in perturb init, we want to pass the information on the error to the local structure, which is ppt. So to summarize, the structure you put here is the one of the function that you call, and the structure you put here is the one of the module where you are when you write the class call. And you only have to remember this. You can forget the rest. And of course, after 10 minutes, you are used to it. You can forget all the rest, and all the error management will be done automatically for you. So this is another example. And here we assume that we are still in perturb init. But in perturb init, we have to call background at tau. It's very typical. Background at tau is an external function of the background module, and it's used to get the background quantities. Of course, the perturbations need to know the background quantity. So if we are in the perturb module and we call background at tau, we don't think too much. We just say, this is a function of the background module, I put PBA. I am in the perturbation module, I put PPT, and it will work. And so I repeat again what will really happen. This function will be called. If it returns a success, we go to the next step. If it returns a failure, we know that the error message has been written here inside this function. It could be written here because it's a background module function. So it always has PBA as an argument. So it has access to PBA error message. So I repeat, if background at tau returns a failure, we know that the error message has been written here, and we copy it from here to the perturbation error message, adding before some automatic information. This is what it does. Is it clear enough? Yeah? Okay. How do you generate your error message? With another macro, which is called class test. I will show you that there are a few others, but class test is the most useful. Class test normally consists in a condition, an error message, and the text produced by the error. You are completely allowed, because macros can take a variable number of arguments, you are allowed in this text to give some precision and numbers. For instance, following the usual C syntax, if you want that the message, the error message contains some numbers, you can use this syntax for integers and doubles. So example, class test, num points. So you should put a class test before any potential error. So in this example, I picked up a line in the code. I think you can find it somewhere. And it says step equal max minus min divided by num points. And when you write this, you realize that you have no control on all what you could do, the mistakes you could do, the mistakes your users could do. And you cannot guarantee that this will always be non-zero. And you are scared by this. So you say, I'm going to put a class test. And then when this is set accidentally to 0, I am safe. The code is not going to crash. It's going to tell me where was the problem. So for this, you put a class test before of num point equal to 0. And assuming that this is in the perturbation module, you want to write the error message to the inside the structure where you are. So this structure here is just where you are. If this class test is in the perturbation module, it's a PPT. And then you put the text that will help the user to debug. And the nice thing is that you should not say here, there was a problem because num point was set to 0, because this condition will be written automatically by the automatic part. So you will know already that num point was set to 0 and in which line. So you could even leave this blank. It would be enough for the user to know that num points was 0 in a given line of a given function. But if you want to be a bit more talkative and suggest how to debug, you can write your debugging suggestion here. Okay, and you don't need to put a /n because a /n, which is back to line, will be added automatically. Okay, so this is how a very short error message here will return a very long and informative sequence, as we have seen before. Rule 5, when you allocate memory, you should also use our macros. So we allocate a lot of variables in class because we always want our array to have the minimum required size and not make a guess of what could be the maximum size of an array and declare it in this form. So all our arrays usually are declared dynamically exactly at the size we need. And usually this is done in C with a malloc memory alloc command, in which you pass a pointer and the size of the region you want to alloc. So in class, instead of malloc, you will use class alloc with the same arguments plus the error message of the structure where you are. Okay, so if you are in the perturbation module, this will be PPT error message. And when the allocation fails, the macro will ensure that everything complies with the error managed format, and you will get this message, in this case, generated entirely automatically. Maybe I can do a summary of all these macros that you find in command.h. If you look now in include command.h, you will find them. They take a lot of lines because for each of them, they are usually about 10 lines. The one in red are the one that you will use more frequently. So the first one are for calling functions. Class call takes again the function, the input and the output error message with the logic we have seen before. For some reason, class call will not work when you are in an OpenMP parallel zone. So the code has, I think, about 10 OpenMP parallel zones. These are loops that will be distributed among the threads of your computer. And for some technical reason, class call is not allowed inside these regions. You will just use class call parallel, but the rest is the same. It does something a bit differently. Class call except can be nice because sometimes you know that in a function you allocate a lot of memory, then you return a failure, and if you don't do anything, this memory is lost and you have a memory leak. So sometimes when you find an error, you would like to execute some lines, which could be freeing this memory, before returning the error and stopping class. And for that, you have class call except. Class call except is like class call, excepted that after the function, you can write a few lines of codes. And you can put, no, this is the last argument. As I said, macros can take a variable number of arguments. So it's not a problem if you have 20 more arguments here. So after passing the usual arguments, you add different lines of code separated by a semicolon. It could be free this pointer, print this, whatever. And in this case, if the test returns a false, first these lines will be executed, and then the rest will happen normally. So normally we should have many more class call except, but we have only put them when we realize that by not putting them we had memory leaks. If you don't put the class call except, the code will work anyway. And if you are not scared of these memory leaks, it's not a big issue. Okay, so this is, say, it's for advanced developers. Class test now. We already saw class tests. It has a condition, the error message, what you want to tell to your user or to yourself, and eventually some arguments to fill up numbers in this message. Similarly, class test cannot work in a parallel zone, so there is a class test parallel and a class test except with the lines of codes. Class stop is used for debugging. Okay, so very often when you do debugging in a code, you write an exit or a quit or something in the middle of the code just after the line you want it to test. If you do this, you can write a break or whatever, but you will lose a lot of information and your code will really stop abruptly. If instead you write a class stop, error message output and your message, then class will exit gently and you will have this tree of dependency of function pointing at the line where it stopped. And it can be nice. So we have seen class alloc. There is also a version for OpenMP, parallel zones. And a class realloc is the same as a C realloc. Class calloc is the same as a C for calloc. So calloc means that not only you allocate a memory zone, but you fill it with zeros. Okay, and to be completely professional on these error management rules, I need to finish by 3 exceptions. So exceptions are never nice. You would like to avoid them, but they are in very special places. So if you forget this, it should not be a big problem for you. Okay, the exceptions for this error management are first, the fact that in the main class.c, we say that class.c has 20 tasks to call the 20 init functions, the 10 init functions, and then the 10 free functions. And of course, the main is going to call this function respecting the error management. And now you understand why, when you look at your main, you can look at it now actually. When you look at your main, you don't have just 20 lines, you have more because of the error management. So for instance, the main wants to call background.init. And we could have used a class call here. We don't use a class call because in class call, there is always a syntax to pass the error management from a lower level to a higher level. And in the main, there is no higher level. So the class call would not work. You don't want to pass the error message to the nesting function, to the higher level. You want now to pass it to the user. And so only in this case, instead of class call, you have some explicit lines which look like the macro class call, but they will just print the error in the standard output. So if background init returns a failure, you print to the standard output that there was an error in background.init, and you return a failure. And so when you run on the terminal and you see an error message displayed, the first line of this error message came from one of these 10 calls, from this printf. There was no printf before, but you need a printf at some point, and it's here. Okay, so in summary, only in this main, there is no class call. All the rest relies on class call. Second, the input module is a bit special. The input module does not have an input structure associated to it. And it complicates a bit the error management because there is not a pointer to input structure, arrow, error message. It doesn't have its own field for error message. So it's not a big deal, and I give the example of some call of functions in the input module. At some point, the input module will call this background function, which initializes the phase space distribution of non-cold dark matter, like massive neutrinos. And also in the input module, you will call some parser functions, and all the parser functions come from a file called parser.c, which is in the tools. So it's not in the module. So we use class call, but the difficulty for this class call is that we cannot write the error in an error message, which is part of a structure. So it's not a big deal because at the beginning of the input module, we declare a string called error message. and it will play the role of the other error messages. So if I am in the input module, I call this function. It's a function of the background. So I know that my input error message is in the background structure. Background, background. I don't have to think. And here, normally, I would put the error message of the module in which I am, and for the input module, it's just this variable error message. Now, here I'm calling a function which is not belonging to any class module. It belongs to the tools. It's not one of the 10 modules. In the tools, there is not this rule of having structures and error messages. So in this case, all these functions which are in tools have their error message as an argument. So in my input module, I have declared this string error message. I class call the parser function, giving the error message as an argument, because then if there is a problem, this function will write its error message in this argument. And then we have it available here. And we are still in the input module, so we copy it here. And it's a bit funny because there is the same variable many times. But the result of this class call is that this error message will contain first some automatic command, and then the error message returned by this. So the error message is growing between here and here. Okay, so this looks a bit complicated, but in fact, it's like the rules we had before. It just says that when you don't have an arrow error message available, you use this instead, and that's all. And the last rule, this is really the most technical slide of the 2 days. So the last rule is the following. Yeah, but it's the same as here. When we call an external function that was not in the 10 modules, we must pass our error message ourselves. So I gave an example of parser function, and here it's an example of an array function. In tool slash, you have all these numerical methods. You have the parser, you have the integrators, and array.c contains lots and lots of functions which do extrapolation, interpolation, and integration and derivation of vectors, of arrays. So here I call this function, which is in the tools. And so this function doesn't have its own structure. So I must provide the place where the error message will be written. And here I assume that I'm in the background module. I do this call in the background module. So I'm going to provide to my function the error message of the background module. It will write its error here. So the error will be here, will be added something automatically, and will be passed to the same field, but this field will grow. And it's the same logic here and here. In both cases, we had the functions from the tools, so we were forced to pass the error message as an argument. But here we are in the background module, so we can use our PBA error message. Here we were in the input module, so we had to use this error message. And now you know all the subtleties of error management, even the worst exceptions. That should be it. Yes. Do you have questions on this error management? So really, it doesn't take much time to get used to it. But for this, a lecture is nice. Without the lecture, you can stumble for quite some time. Yeah. So ask questions if you're not sure about something. Okay? Very good. So what do you do when you want to implement a new feature in the code? So I will just give some guidelines, because the message here is you don't need to know anything for that or to remember anything. When I say implement a new feature, I mean you want a new matter species, or maybe, and this was your question before, you want to implement a new approximation scheme, or maybe you want, I don't understand what I meant there. A new mathematical description of an existing species, switching on more precise corrections, etc. Ah, yes. Well, it's very badly written. So you want still to use the same species, but with different equations. Okay. Or you want to implement a new observable. So for instance, you want to code a new type of CLs, or you want to code the cluster mass function, something new. So all these are new features. And for all these kind of new features, it's always the same logic. Think of a name, think of an acronym that summarizes your feature. And a good acronym is something that you can easily search in the files or with a grep. So for instance, here, suppose you want to code early dark energy. That's for the John Hopkins people. Don't call it EDE, because if you search for EDE, you will find it all over the place in words like this. So find an acronym very specific, like early EARDE should be good. Then think of a feature close to your feature. So if you want to code a new matter species with fluid-like equation, start from the fluid. With Boltzmann-like equation, start from the neutrinos. You want to implement a new approximation for the perturbations, start from TCA, tight coupling approximation. You want to implement a new way to compute the power spectrum, you will find somewhere an acronym for that. Then you grep or you search for all the places in which there is FLD, and if the previous acronym was well defined, it will go quick, it will be unambiguous, and you will find mainly that there are regions with an FLD. There are maybe 20 regions with an FLD in the code. And if you want to be more specific, you can just search for has FLD, because anything related to the fluid is inside some bracket after an has FLD. This is the power of these flags. So you can grep, if you want now, for has FLD in all the C files, and you should get of the order of 20 of them. And you know then that you have to, for your new field, to care about these 20 things. Then you duplicate each of them, and of course you replace in the duplicate version FLD by ERDE. And then you just have to think of what is different in the initial one and in the new one. And very often it will be just a couple of lines because you want a different equation of motion, for instance. And the rest will just be some query replace of FLD by ERDE in all these zones. So it can go very fast. And the advantage is that you don't need to think too much, okay? You don't need really to understand everything about the structure of the code. You say, oops, they did this. I'm not sure why, but I will do the same. And this is the equation that I need to change. I change it. This is how I do myself, because you cannot remember the details of so many thousands of lines. Okay, so there will be exercises where you will add a new feature, and I hope it will go quickly. I'm close to the end, so as I told you, this will be less than 1 hour. I want to talk a bit about the Python wrapper. So the Python wrapper is located in your Python directory, inside the class directory. And the most important files are classc.py and cclassc.pxd. There are lots of other files. For instance, there is a setup.py, which is used when you compile at the beginning to install the module, classc. There is a test, which is used for testing the module, the wrapper. And then there are lots of files which are written automatically at compilation. And you don't want to touch these ones. If you did, they would be overwritten by the next compilation anyway. So these are the important files because they are not generated automatically. On the contrary, they are used to generate automatically the other ones. So these two files are written in Cython, which is this language that does the interfacing between C and Python. But it looks very much, essentially you only have to declare things. The syntax is very simple, and you just have to look at what is around to understand the syntax of Cython. So why would you need to edit it? Well, it's because if you have coded new parameters and new features, if you don't tell the Python wrapper that they are there, the Python wrapper will not understand your new input parameter. So once you have finished your modification in the C code, you have to propagate it to the wrapper, but usually this will be as simple as adding 1 or 2 lines. Let me be more specific. So in this file, cclassc.pxd, there are only declarations of variables and of functions. So for instance, if you look now at cclassc.pxd, you will see a cdef struct background. You understand that this is where you declare the structure background, because the logic of Cython is that you need to redeclare everything that was in the C code and that you want to know in the wrapper. So struct background was of course declared in background.h, but now the wrapper will understand this structure only if it is redeclared here with a cdef. So cdef and semicolon, and after you have several variables declared like in the C file. The only difference is that in the C file you would have a semicolon here. Sorry, this is just a column. Okay, so do you need here to redeclare all the variables of the structure background? Not necessarily. You only need to declare the ones that should be known by the Python module. So for instance, the age of the universe in gigayears is something you want to know in the Python wrapper, because you have this get-derived parameter, and you can have a get-derived parameter of age, and it will give you the 13.8 gigayears. So for this, you need to declare it. But if there is a variable of the background structure that the wrapper doesn't need to know, there is no need to declare it here. And fortunately, we know that the Python wrapper is only interested in variables which are in one of the 9 big structures, because all the code has been designed in such a way that all what you need to know about a module from outside is a field of one of the 9 big structures. So you can be sure that you don't need to declare any other variables than those in the 9 structures. Otherwise, it would be scary, but all the interesting stuff is there. Okay, so let's assume you want to add a new species that we will call presidential dark matter. And you need to find an acronym. So here it's Trump. And in include background.h, it means that in the C code, in your structure background, you have a new variable, double row Trump. It means that in cclassc.pxd, you need to declare a new variable with the same name. And then it will be accessible to the wrapper. After that, you want to recompile everything. And I take this occasion to say that the make clean is really important, because, for instance, when you redo make without a make clean before, the wrapper is not recompiled fully. Make clean is important, especially to be sure that the wrapper is recompiled. So the rule, in fact, is that make clean before make is important in 2 cases. When you have changed something in one of the .h files, or when you have changed something in the wrapper. The best is to do it every time, and then you are sure you don't have a problem. Okay. Now, yesterday I got the question on the samplers. So you have a lot of choice if you want to use class inside a sampler. So the sampler that we developed from scratch in our group is called Monte Python, of course, for Monte Carlo in Python. It was started just after releasing class by a previous PhD student, Benjamin Audouin, who has left physics now because he loved this so much that he wanted to become a software developer after. And then it has been maintained by lots of people, including me. I mean, he did it under my supervision, so I kind of remember all what is in the code. And recently, my previous PhD student who finished last year, Thijs Brinkman, who is now in Stony Brook, has taken the lead, and he's the one supervising the updates and answering questions when you raise issues on the Git. So there is a private repository, MontePython private, which was always in my GitHub that you cannot see. And the public repository was initially in the GitHub of Audrin, but is since a couple of years in the GitHub of Thijs. The one with Audrin here is obsolete. You should never use it. Okay, so it does essentially the same as Cosmo MC. Actually, it has more functionalities. I can comment briefly on the differences. In Cosmo MC, you have to use a version of the Metropolis hastings algorithm always. In MontePython, you can choose between Metropolis hastings, multinest, and Cosmo Hammer, which is a version of EMCE for cosmology. Honestly, usually I run in Metropolis hastings. Every time I try the other, I'm a bit disappointed by the performances, but some of my students are fan of multinest and think they get better results with multinest. So you can choose at least. The versions of Metropolis hastings, which are in Cosmo MC and in MontePython, are slightly different. There is one aspect which is more elaborate in Cosmo MC. It's the shape of the probability distribution that decides the next jump. And there is one aspect which is more elaborate in MontePython, which is an adaptive, an automatic adaptive sampling that will automatically adapt the jump size. So if you are familiar with either MontePython or Cosmo MC, you know that to get good results, you must pass to the code a covariance matrix obtained from a previous run and a jump size. And for the jump size, there is a magic number, which is 2.4. It's a default in both Cosmo MC and MontePython. And this jump size tells you by how much you must multiply the number that you draw from the covariance matrix when you do a jump. This magic number 2.4 is known to be optimal for multivariate Gaussian posteriors. When you don't have a multivariate Gaussian posteriors, the optimal number that will give you a nice acceptance rate can be quite different from 2.4. For instance, I remember that with Planck 2013, it was 1.6, and Planck 2015, 1.8. It changes every time. It has to do with the fact that the nuisance parameter, in this case, are very much non-Gaussian distributions. So each data, and it combined with each model that you may try, has its own optimal number for the step size. And in Cosmo MC, you must still do a guess and use a default or use your own value, but it will not change. It will only change in the next run. In MontePython, it will be adapted automatically. And this is really important. You might think that adapting the covariance matrix is degenerate with adapting this number, but it's not degenerate. Both codes will adapt automatically the covariance matrix during the run in the same way. But on top of this, one will fix the jump size, the other one will adapt the jump size, and it's really completely different, and it really boosts the convergence. So I think we have much faster convergence with our Metropolis hastings thanks to this feature. Okay, another difference is that MontePython has its own plotting tool, because you can run MontePython in MCMC mode or in plotting mode. So you can do nice plots with MontePython. This is an example. You can customize lots of things. You can choose how the smoothing is done here. This is from a recent paper we did with Thijs and others and Boris Boliet. I acknowledge that I don't know a better plotting tool than the getDist of Anthony Lewis, but that should not stop you from using MontePython, because MontePython writes its chain in the same format as Cosmo MC. So you are free to run with MontePython and plot with getDist if this is not good enough for you. Okay, so this is one. And the second one I want to advertise is Cobaya. So Cobaya has been released recently, and there are still some updates taking place now by Jesus Torrado. So Jesus Torrado is a good friend of both Anthony Lewis and myself. He has collaborated with both, and he wanted to write a very modern Python code, even more modern and fancy than MontePython. And he did it keeping in touch always with both Anthony and myself. So his code is compatible with both class and comb. And I would say the overall structure of Cobaya is much more inspired by MontePython than Cosmo MC, but with some nicer features, like the fact that you construct all your input in YAML files. That's very nice. The way in which it installs automatically is very nice also. So Cobaya is supposed to become the successor of Cosmo MC, and it does everything that MontePython does, more or less. So I think maybe we will switch to Cobaya also, and I'm already using Cobaya for some purposes. But for the moment, the idea is to keep maintaining MontePython. There are things still that MontePython does and the other don't do. For instance, this adaptive steps that I mentioned is only in MontePython so far. MontePython has some very nice features for doing forecasts. So the MCMC forecasts. If you want to do an MCMC forecast instead of a Fisher matrix forecast, MontePython does lots of steps automatically for you. If you write the likelihood in a given format, it will automatically generate some mock data before trying to fit it. This is very nice, actually. And we do lots of MCMC forecasts with MontePython. So far, this is only available in MontePython. But I think that with Jesus, we want to put it at some point also in Cobaya. So I'm less familiar with Cosmosis by Joe Zuntz. I just know that it's a great code. I can only say good things about it. All the people who use it are happy with it. I don't know the details of how it's interfaced with class. I just know that it is also fully compatible with both COM and class. If you are a frequentist, if you are a bit skeptical about priors and these kind of things, you can use a very nice algorithm developed by people who are very good in coding too. It's called Camel. It comes from a group in Orsay that contributed to Planck. It's in C++. And when you want frequentist bounds, what you need to do massively is minimization in a high dimensional space. And this is horribly difficult. There are some minimizer in MontePython and Cosmo MC, and they are both terrible. They never find the true minimum. Okay, so these guys are relying on a very powerful minimization software called MinWit that was developed at CERN for analyzing LHC results. And they call class through the C++ wrapper that you have downloaded with class. This is why this wrapper was developed. So it works well. It's not too slow. Also, when you want to get a profile likelihood, when you want to minimize, to fix one parameter and minimize over the others, you need to run your Boltzmann code at a higher accuracy level than for an MCMC. In an MCMC, if your code does small errors, they will average out. You just have to check that the error is not too big, and you get nice posteriors. In a frequentist approach, you try to minimize something, and the numerical error produces small wiggles on the function that you try to minimize, and the minimizer could remain stuck in one of these wiggles. So in the Camel code, when they call class, they have to call it with higher accuracy settings, and so it's a bit slow. But it still works well, and they have used it in many papers. So I can only recommend it too. Very good. So one last point I want to make. This is a big difference between all the codes that I'm advertising here and Cosmo MC. These codes are completely generic. They know that they need to call a simulator, sample parameter space, and output some chains. But they don't know that it's doing cosmology. They don't know the meaning of any parameters. And the cosmological parameters are never declared in any of these codes. I'm not sure about Cosmosis, but at least MontePython, Cobaya, and Camel. And this is very nice because it means that when you modify, so first it means that MontePython or Cobaya are ready to run with any cosmological parameter that class knows. And if you add a new parameter in class, you don't need to do anything to these codes, because what these codes do is read in the input file the name of the parameters you want to vary and the range, and then they call class with these names taken from the input file, some values, without any redeclaration, interpretation, dictionary, whatever. So you don't need to modify MontePython and Cobaya if you add new parameters or if you want to vary any class parameter existing already. Okay. So that's actually a very nice feature when you have used both codes and compared, you realize that it's a very nice feature. Okay. And I think I'm done. So.